Hello, my name is James Wash, and I'm a physics math double major here at Trevecca Nazarene University. I would like to present to you the subject of my senior seminar project for mathematics, an algebraic examination of the 12-tone system. The 12-tone system is a method of music composition for atonal music, that is, music written without it being in a certain particular key. This is done using tone rows. A tone row is basically just any sequence of the 12 musical tones that uses each tone only once. 12-tone music is built entirely using one tone row and different transformations of that tone row, like playing the row in reverse, inverting changes in pitch, or transposing or moving the row by a number of semitones or steps up and down in pitch. A transformation can also be any combination of the previously mentioned transformations. For my project, I decided I would try and describe some properties of the 12-tone system in the rows it creates using abstract algebra. My research relies heavily on something called groups, which is an algebraic structure. A group is a set of objects along with an operation that you can use to combine two of the objects together to get a new object. A group also has a few special properties. Groups are closed, so combining two objects in a group can't create an object that isn't in the group. Groups have an identity, which is kind of like a zero for addition. Just like how adding 0 to a number doesn't change the number's value, combining an object in a group with the group's identity doesn't change the object. One thing I've been able to do is show that a tone row and all of its transformations can be thought of as a group. If you take two transformations in the tone row group and you add their transpositions together, their shift in pitch up or down, and you combine their other transformations like reverses or inverses, then you will always get another transformation in that group. In this case, the normal tone row we first composed, or the prime row, if you will, is the identity, or the zero of the group. Another thing that I've been able to show is that the row group is abelian. That is, it doesn't matter what order you combine the tone rows in, you'll get the same result either way. One aspect of the 12-tone system that I found interesting was symmetric rows, or tone rows that you can transform in some way and get the same row that you started with. For example, if you reverse some rows, such as the row presented in this slide, and if you reverse them and you transpose them 6 semitones or 6 steps up or down, then you will get the same tone row that you composed in the first place. I was able to prove several results that deal with symmetric rows. For one thing, symmetric rows can only be equal to themselves under a combination of transposition and reversal, or a combination of transposition, reversal, and inversion. One proof of this was already known, but I was able to prove it a second way using the grid notation commonly used by tone row calculators. I was also able to prove that a symmetric row can only equal itself in one specific way, or two different transformations of the prime row cannot both equal the prime row. Probably the most interesting thing that I did with symmetric rows, at least the most interesting thing to me, is that I created a new notation system that allows you to see quickly if a given tone row is symmetric or not. I call this notation system an interval tuple, and it is a sequence of 11 numbers. These numbers represent the difference in pitch between two adjacent notes in the tone row. For example, if the first note is an A and the next note is a B, we will write down 2 in the interval tuple, because there are 2 semitones or 2 steps between the notes in that row. There are 2 types of interval tuples that I have described: an absolute interval tuple and a directed interval tuple. An absolute interval tuple is just a list of numbers. Each one represents the smallest number of semitones between 2 adjacent notes in the 12-tone row. If an A came first, and a G came second, we would write a 2 as the interval rather than 10. Because while you could get from an A note to a G note by getting higher in pitch by 10 semitones or 10 steps, you could also get to a G by lowering pitch by 2 semitones or 2 steps, and 2 is less than 10. A directed interval tuple is similar, but the numbers will be positive if you would have to rise in pitch to reach the next tone, and negative if you would have to lower the pitch. The magnitude is again the smallest number of semitones between two adjacent notes in the 12-tone row. If an A came first and a G came second, we would write the interval as -2 instead of +10, because 2 is smaller than 10, and A would have to lower its pitch by 2 semitones to get a G. If a G came first and an A came second, we would write the interval as +2, because G would have to raise its pitch by 2 semitones to reach an A. This notation made it easier to prove several results. If the absolute interval tuple of a tone row is palindromic, that is, if it reads the same way forwards and backwards, then we know it is symmetric in some way. If the directed interval tuple is palindromic as well, if it reads the same forwards and backwards, then the tone row is symmetric under a combination of reversal, inversion, and transposition. If the directed interval tuple does not read the same way forwards and backwards, then the tone row is symmetric, but under a combination of reversal and transposition. This is certainly easier and faster than trying to figure out if a tone row is symmetric by writing down all of its possible transformations and seeing if any of them equal the prime row. I also did some work examining the 12 permutation group, which is the group whose set is all possible sequences of 12 objects. I think it's pretty easy to think of each tone row as a permutation of the 12 tones of the musical system, as a reordering of the 12 tones of the musical system. So this was a pretty natural comparison to make. Ooh, almost dropped my script. Other researchers have already found ways to describe rotation, inversion, or transposition in the 12 permutation group. So I decided to look in a different direction and try to find interesting subgroups or structures in the set of all permutations of 12 tones. So far, I haven't really been able to. Tone rows don't form groups with their transformations in the permutation group. I've also tried to find groups or structures related to symmetric rows, but I haven't been able to either. Symmetric rows aren't closed in the permutation group, so you can combine two together and get a non-symmetric row. Similarly, you can combine two non-symmetric rows together and get a symmetric row. Generally, it seems like a composition of permutations won't create interesting symmetry-related structures in the permutation group. There are some avenues of research into the 12-tone system that I would like to share, so I or someone else could research them in the future. While I couldn't find any, there may still be interesting subgroups and structures in the 12 permutation group, and it may be useful to look into the group more. My professor actually recommended looking at different ways that permutations can be combined, and seeing if alternative operations may create interesting structures. This may prove a fruitful avenue for future research. Another possibility for research deals with dodecagon representation of tone rows. One paper on the 12-tone system has demonstrated a way that tone rows can be represented by drawing paths around 12-pointed shapes, or dodecagons. While I haven't been able to look at them in depth yet, as I'm recording this, I have found some interesting patterns in dodecagon drawings. I believe that they can be used not only to create tone rows and symmetric rows, but they can also tell us which ones are possible and which ones are impossible. By closely examining a diagram, I believe we can determine what operations a tone row is symmetric under. It seems that if a dodecagon representation is rotationally symmetric, then the tone row associated with that diagram has a reversal symmetry. And if the dodecagon representation has a reflective symmetry across some line of symmetry, then the tone row that is associated with that diagram has a reverse inverse symmetry. This could also be an interesting result to try and prove, and provide another way to quickly check if a tone row is symmetric or not, and how it is symmetric. Another major avenue of research is in cyclic shifts. Some composers use another transformation called a cyclic shift, which basically takes notes off the end of a tone row and attaches them to the beginning of the tone row as a transformation. I haven't done any work or focus on cyclic shifted tone rows or transformations, because if I were to include it, research on this would become substantially more complex than it is right now. Doing research on tone rows under the more general cyclic shift transformations could be interesting and allow for wider understandings of the 12-tone system. I also think it'd be interesting to try and apply what is mathematically known about the 12-tone system to compose atonal music using 12-tone systems, such as maybe certain elements of a group could be used together. Working on this project was really interesting, and I'm glad I was able to share it with all of you. Have a great day!